Hey everybody, today we will do another video and it's going to be a continuation in the using the differential equations to solve circuit problems, and but it's going to be application based now. Like we learned last time about the differential equation that is equal to 0 on one side, which is a homogeneous type, and then we had the second derivative, first derivative, and the second derivative on the first part doesn't have any variables. The second derivative has the variable r over L over 2L actually, but we will actually do it without having to solve that at the moment. It's going to be just application based. And then we had a capacitor and the inductor at the end, right? So that basically was the differential equation that we actually had, right? So now we will have to see, right, how this works by doing some examples, and it is going to be, kind of simple, not going to be too complicated. However, I think I need a calculator because I need a calculator for this because it's going to be some decimals involved. Okay, so let's get started. So we have a problem, right? So we have a problem that it says in figure 8.8. So we'll see that figure 8.8. So 8.8, we have something like this, similar to the example that I gave last time. But it says in figure 8.8 we have a circuit like this. It is a short circuit. Doesn't have any voltage source in this case, but it has a resistor, and then it has an inductor, and then it has a capacitor, and then it has a current going like that. It's a current I, right? And then right here we have, coming back to the source. So in other words, this is a type of circuit that it seemed like it's already, in a short circuit, which we don't have to do anything basic. If we had a voltage source over here, we can short it, but in this case, there's nothing. But obviously, it's voltage going around because that's how electricity works. Unfortunately, you gotta have voltage, current, and resistance. So it says the problem says that in figure 8.8, the resistor R is 40. R is equal to 40 ohms, and in the inductor is 4 henries. L right here is equal to 4 henries, and in the capacitor is equal to 1/4. C is equal to 1/4 of a farad. And a farad usually would normally write with a capital F. Okay, so we have the values, right? Now our first goal is going to find alpha. In the case of finding alpha, which from last video we learned that alpha is equal to R over 2L, right? 2L. And from here we know that L is equal to 4 Henry, right? So now and R is equal to 40, so this alpha right here is equal to 40 over 2 times 4, which is equal to 40 over 8, which is equal to 5, right? And notice that 5 is simply because we have an ohms over ohms. Well, technically, if somebody can say, well, what about real resistance? Well, we're not doing that right now. We're just evaluating problems because Henry it's a unit of Henrys, but technically we're dividing resistance by the unit of Henrys multiplied by 2, right? So in that case, we're not finding impedance right now. We're not worried too much about that case, right? So basically, so then we have the other, so we found now alpha. Now we need omega naught, right? And omega naught is equal to 1 over the square root of omega naught times C. No, LC, right? So LC, right? So in that case, what we're doing is, so we know the values for omega, for L and for C, right? So now we find omega naught by saying that 1 over the square root of those two guys, which is technically in this case, right? So we have L, right? And we have a C, and then we have L is equal to 4, right? And then it's equal to 1/4, right? And C is equal to 1/4, right? Right? So beautifully right here, right? So in this case, what we can do is simply use our techniques of algebra, right? And what am I doing over here? Well, I mean, even though it's under the square root, but it still works. Maybe third grade math. We can go back to that, right? And then we got the following. So we got the square root of 1, right, over 1, which is 1, right? And that is equal to 1. Okay, so now we have a values for omega naught, right? And then we have the value for alpha. Now, what did we say last time? Well, we said last time we have 2 cases, right? We have 3 cases actually. And one of the cases says that if omega naught is greater than if omega naught, right? So if S1 is equal to this, plus, right? Minus alpha, right? Plus alpha plus alpha plus alpha square minus omega naught square. So in this case, we know that if alpha is greater than omega naught, right? We have an overdamped case. So in the case of that, we have an overdamped case, right? So now, what is the, somebody can say, well, what will be, the analysis that we're doing, right? Well, so in this case, because alpha, in this case, is greater than omega, we have an overdamped case. So because right here you say S1 is equal to alpha is equal to 5, right? Negative 5 in this case, and then plus the square root of 5 squared minus 1, right? 5 minus 1, which is equal to minus 5 plus the square root of 24, right? Because that square is equal to 1, that square is 25, so 25 minus 1 is 24, and then when you do the math on that, you know it's going to be less than 5. It's going to be, because the square root of 5 is 25, so this is going to be about 4.9, all right? So in this case, it's going to be 4.9. So 4.89, right? Very close. So 4.89, right? Very close to 4.9, right? Now, notice that I have that positive right here, right? But I have right here, let me just, I don't want to create confusion because that 5 is close to that right there, but this is 5, right? Negative 5 plus 4.89, right? Now notice it when I add those, it's going to be a negative, right? So negative 5 plus the answer is negative 1. So S1 in this case is negative 0.1010. Very small, right? So that's S1. So notice that we had a value, and that value that we had when the square under the square root was a positive, so we still had a value was a negative, but it was not imaginary value. That's basically, a good thing because we don't have to deal with complex numbers. So that is S1, right? Now what about S2? So S2 similarly, right? So similar in S2, so if S2 is equal to, right? So now we're looking at minus, right? But also we're looking for a minus right here because we used the plus already, right? So now we're looking at 5 squared minus 1 squared, right? Now when we do that, we have S2 is equal to minus 5 minus this guy right here, which is going to be the same thing, which is going to be, when I do this, this is equal to a positive, but I carry the negative sign, which brings me to which bring me to what? 4.8989 again, right? Now adding those two is going to be equal to negative 9.8989, right? So now these are the two values, right? So I have the S2 value and I have my S1 value, when we can conclude that the values inside the square root still were positive, which means that we have an overdamped case. Overdamped case, right? So we came out with the answers and we have an overdamped case. Why? Because alpha was greater than omega in that case. Now, so that's one of the cases, right? So the next case, we will do another one and see what we can do real quick. These problems are not really bad. They just requires a little bit of knowledge of the formulas and kind of basically get the information that you need, and from the information given, right? So, okay, so in this case, R is equal to 10. So in this case, R is equal to 10 ohms. L equal to 5 henries. And C is equal to 2 microfarads. Right? So microfarads is basically actually it's millifarads. So it ends is millifarads. So which means that is 10. It's 2 times 10 to the minus 3, right? So okay, so let's do it. So in this case, what we do, the same thing, right? So we do what? We do alpha, right, is equal to 10 on the top, which is alpha is equal to R over 2L, right? So alpha is equal to 10 over what? Over 2 times 5, right? Which is equal to what? Which is equal to 10 over 10, which is equal to 1. Right? So that's pretty simple, right? Now let's do the omega and see what we get. So now omega naught is equal to the following. Omega naught is going to be equal to 1 over the square root of LC, right? Now omega naught now is going to be the following. It's going to be 1 over, and right here is when we have to use the little operation that we need to do, which right here is 5, right? And then multiply that guy by 2, right? By 2, but that 2 gets multiplied by 10 to the minus 3. Why 10 to the minus 3? Because of millifarads, right? So now when we do that, we get 5 times 2 times 10 to the minus 3, right? and then I take the square root of that, right? And then, so this guy right here is actually 1 over 0.1, right? And it's equal to 10. Okay, so now, you can see it right now, right? You can see just by analyzing this, now you see that S1 is equal to negative alpha plus or minus, right? In this case, plus or minus alpha squared minus omega naught squared. Now you can see that omega is greater than alpha, right? So which means that you know where we're going in this. So S1, like for example, in this case, when you evaluate it, it's going to be alpha is equal to 1 minus, right? Or you can say plus, and then we do what? And then we do alpha is 1, right? Minus 10, right? Square, which is going to be equal to what? So it's going to be equal to what? It's going to be equal to minus 1 plus right here. So it's going to be right here. You got to be careful because technically what we're doing right here, we add these two guys, right? That is square is 1 and that square is 10, which is 100. So right here we have 1 minus 100, which is 99, right? So minus 99, so it's equal to negative 1 plus the square root of 99 negative, right? And of course you cannot take the square root of a negative, but you can replace that negative with a j because it's an imaginary number. In electrical engineering, we don't use I, we use j. So, right? So taking the square root of that guy, it's going to be very close to 10, right? But it's going to be like 9.9999. Of course, you got to take the square root of negative. So it's 0.9498. Okay. So this is, so technically this is 1, right? Plus, and remember that this is a value, right? So eventually, when we do AC analysis, this is a value that's given for the cosine part, like the real part of the whatever we're analyzing to, right? So, but this in this case is going to be equal to 9.9498, something like that, and that is J. We put a J in front because it's a negative. It's a negative number, right? So that's so that is the first, right? Now, so what is technically the solution for this one? Well, technically the solution is the following. So the solution is alpha, right? The value of alpha, which is 1, comma 10, right? And the omega is 10, alpha omega, and then on top of that we have which is what I found right here, which in this case is minus 1 plus 9, and then 9498. I think it's 9498. Right? So this is the answer, right? Right? So what do we have? We have technically, in other words, we have this. So So we have something like this. So we have, like, let's say for example you have I of t, right? So, or v of t, whatever. It doesn't have to be I of t is equal to cosine of omega naught t, right? That's what we have right now, right? Plus j sine of omega naught t. That's what we have, right? So we have, this is the cosine, the sine part, and this is the cosine part. Ignore that the cosine is negative. So this is a good thing to understand circuit eventually, because now let's say for example you are asked to find from here the angle, right? So you take, assuming that this is y, this is x, I'm sorry, and this is y, and then to find the angle, which is eventually, I think I have done some videos about rectangular coordinates and about going back and forth to polar. So if you want to find the angle, so you do tangent of theta, right? And then you can say that same tangent of theta, right? Tangent of theta is equal to y over x, which is technically saying sine over cosine, right? And you take the inverse of whatever those values are, and then you get the angle of that guy, of this. So eventually we will do some problems, more problems, because I know I done some, like, some problems like this before in this channel, but in this case that is the solution for that, which we have in this case. In this case we have an underdamped case, right? So we have an underdamped case, right? So we have this. This is the solution for this, actually. You can say solution in analysis, because we analyze that it's an underdamped case because with an imaginary number, right, that we got, and it's, unfortunately, when you got negative inside the square root right there, you don't have other options but go with the imaginary numbers, and then imaginary numbers turns into trigonometric identities like this guy, and that's how we do these problems. And I see you in the next video.